Good morning, everyone, and welcome to the Energy Pathfinder webinar on the energy efficiency of the fabric of buildings. We have our key speaker today is Caroline Rye, who will be introduced in a moment by Carsten from Historic Environment Scotland. I'd just like to give a brief introduction to the Energy Pathfinder project. It's a Interreg Northern Periphery and Arctic project. It has run for 1 year now, and it'll be running until 2022. And the aim of the project is to look at approaching near zero energy in historic buildings. It includes 6 partners from 5 countries, 2 from Ireland, 1 from Scotland, 1 from Finland, 1 from Sweden, and 1 from the Faroe Islands. And in each one of these countries, there is a demonstrator. In the case of Ireland, there's 2. These are historic buildings that we're actually looking at the feasibility of improving them to something approaching near zero energy, and also looking at the energy management in the buildings once they're completed. The lead partner is the University College of Cork, Cork Centre for Architectural Education, and I am the project manager on their behalf. The particular webinar that you're listening to today is under the auspices of Historic Environment Scotland, our Scottish partner, who are responsible for the energy management and energy efficiency aspects of the project. And Carsten will talk a bit more about that. The webinar series is, this webinar is one of a series of webinars that the project is organizing. We've already had 2. This is our 3rd, and they're organized by NC Energy Hub, who are the dissemination partners for the Energy Pathfinder project. Just a few words on, while we let the rest of the partners in that are waiting there. Just a few words on the logistics of the session today. We have a presentation that will last something like 40 minutes. You're welcome to ask questions, but we'd like you to enter the questions into the chat facility, which you'll find on the bottom of your screen. So if you please write your question there, they'll be taken in order after the presentation is completed. And we will ask you to unmute your microphone in order to ask your question directly to the speaker, and we'll deal with as many questions as possible before the end of the seminar. Now, I think without, we've actually got a good number of people now, 18 at the moment. So we'll open the main session. I'd like to ask Carsten from Historic Environment Scotland to introduce the speaker. Thank you.
Good morning, everybody. Lovely good morning here from Edinburgh in Scotland. I'm Carsten Herman. I work with Historic Environment Scotland, which is the public competent authority on cultural heritage. We look after many historic buildings in Scotland and provide policy advice. Our role is quite wide, includes listing and scheduling of historic buildings, informing Scottish Government on how to shape up policies, but we also look after, on behalf of the Scottish Government, after about 330 sites in Scotland, including Edinburgh and Stirling Castle. And as part of this overall duty, we also conduct research, technical research into repairing and conserving historic buildings, historic building fabric, and that includes energy efficiency. And we've been involved in a variety of European projects, including Adapt Northern Heritage, Advanced LEMIS applications, and Ephesus. And we are really delighted to be partner in Energy Pathfinder, the project which is sponsoring and organizing this webinar today. Our previous research into energy efficiency of historic buildings has kind of started with looking in detail at the usefulness of U values and how to factor them into building performance calculations. But we've moved on and have been more looking at humidity and moisture in combination and how that affects particularly older buildings which are vapor open and are therefore heavily impacted by retrofit, particularly through insulation. As part of that, we've had trial projects, one of which is actually in our own estate in Holyrood Park in Edinburgh. The building concerned is Holyrood Park Lodge, a small lodge building. One of the sites where we've involved ArchiMetrics, a company from the south of England, and a company which was co-founded by today's speaker. And I'm very joyful to introduce today Dr. Caroline Rye, who has been working with us for quite a number of years now, probably a decade. She has a master's in historic building conservation from Portsmouth University and a PhD from Napier University here in Edinburgh. She has, as I said, co-founded ArchiMetrics, which is a company working on building performance research. And for us, they've been heavily involved in environmental monitoring, especially in the form of interstitial monitoring of building fabrics. So understanding how moisture and humidity move around in building fabric, in stone walls particularly. Caroline is a member of the technical panel of the Society for the Protection of Ancient Buildings, a technical expert of the Sustainable Traditional Building Alliance, and now also involved in drafting the building performance standard for the British Standards Institution. So without further ado, I would like to invite Caroline to give her presentation on building performance and monitoring, and particularly how we've done that at Holyrood Park Lodge.
Thanks, Carsten. Right, I'm just going to share my screen with everyone. Hi, everyone. Which one shall I use? That one. Okay, so hope everyone can see that. Yeah, and everyone can hear me. So off we go. So Carsten gave me a really, oh, hang on, what's going on? I cannot, Carsten gave me a really nice introduction. So I'll try not to repeat what he said. But just to say that we're a really small building performance research company, and it's just me and one other person, Cameron Scott. We were founded 9 years ago with the aim of improving the understanding of building performance by making in situ measurements. So that's measurements within actual real life in use buildings. So retrofitting presents lots of opportunities to improve the comfort, the usability and the energy performance of traditional buildings. However, because it's also a field that can present risks to both the building fabric and the occupants. And that's in part because some of the materials and techniques commonly used in retrofitting may prove detrimental to the fabric and to internal living conditions. But also because as this is actually a relatively new field, there is limited information available to inform design decisions. And this picture is further complicated as the performance of buildings is highly dependent upon their specific circumstances, including what they're used for, where they're located, the materials involved in their construction, their orientation, their exposure, and their state of repair. So through the investigation of the performance of buildings in the real world, we aim to provide knowledge that can aid building design, optimization, and management practices to enhance the quality of our built environment. Monitoring and measuring building performance, be that heat, moisture, air leakage, air quality, comfort, the list is potentially endless, allows us to move away from the assumptions that might be made about older buildings, such as heat loss is worse in an old building or old buildings are drafty. And it allows a more informed approach and allows retrofit thinking to move from the generic to deal with the more nuanced, specific circumstances of an individual building or set of buildings. Monitoring can give confidence to design decisions. It can be used to test experimental treatments prior to a wider deployment. And after retrofitting is complete, it can be used to keep a check on performance over the long term, to see the effectiveness of improvement measures and to watch out for adverse reactions. So some of the techniques I'm going to show you, we've pioneered and developed ourselves, including designing and building the instrumentation. And then some of the methods are more widely known and available. And in the context of this talk, I'm going to talk about in situ U-value measurement that Carsten mentioned, so that's heat loss measurement, interstitial hydrothermal gradient monitoring, which basically means measuring temperature and relative humidity through building element sections. And both those measurements are undertaken over time and the data recorded to data loggers. And then there are other shorter term measurements such as air pressure testing and thermographic surveys, which should be more familiar to people. And to illustrate this, as Carsten said, to illustrate how some of those techniques have been used in retrofitting, I'm going to talk about this building in Edinburgh, which is Holyrood Park Lodge. It's owned and operated by Historic Environment Scotland, and it's been subject to a programme of retrofit. So the lodge is a Category B listed Victorian building. It was built as a dwelling in 1857 to house the constables who police the Royal Park. It's sited at one of the entrances to Holyrood Park. It's opposite the Palace of Holyrood and it's just across the road from the Scottish Parliament. So one of the first measurements we made at Holyrood was of wall U values, and that involves fixing a heat flux sensor, measuring heat flow through a wall to the interior surface, while also monitoring internal and external temperatures. So these measurements ideally need an average of a 10-degree difference internal external temperature. So in the UK, we can actually only really carry out these measurements over the winter. An assessment of heat losses from individual elements, so that can be walls, floors, roofs, can be useful, if not crucial, where insulation is being introduced to some of these elements. It's particularly the case for solid walls, where research, some of it, as Carsten alluded to, which was carried out by Historic Environment Scotland, shows that a standard U-value calculation can exaggerate the amount of heat from an unimproved wall, the amount of heat lost from an unimproved wall. So we measured this wall at Holyrood twice over 2 different winters, and we arrived at a measured U-value of 1.07 watts per meter squared Kelvin, which shows lower heat loss than its calculated equivalent. And having a more accurate idea of heat loss allows you to specify more precise quantities of insulation in order to achieve desired improvement targets. And where interstitial condensation is a concern, which it should be for all internally insulated solid walls, an accurate U value that doesn't, like a calculation, overestimate heat loss means you can avoid overcooling the wall and thus decrease the likelihood of condensation forming within the fabric. Furthermore, if energy consumption modelling is part of your retrofit processes, utilising measured in situ U values means the model is more likely to predict more realistic energy, cost and carbon savings than the use of the default software input values. And modelling for comfort improvements will also benefit from the use of real site data for similar reasons. The walls at Holyrood have an internal lining constructed from lath and plaster, which is set off from the stonework by battens, and that batten space creates a gap of about 40 mil. And as part of its retrofit, cellulose fibre was blown into that space between the lining and the stonework to internally insulate the wall. So we measured the U value for the wall once it was insulated, and we found an improved U value of around 0.65, which equates to a 39% decrease in heat loss for the wall as a result of this relatively modest intervention. So I've already mentioned this matter of interstitial condensation as a particular concern for internally insulated walls. Although with solid walls, we also need to bear in mind other sources of moisture such as rain, especially wind-driven rain, groundwater, and escaped water from building failures and flooding. As I'm sure you all know, the thought is that if one adds insulation to the internal surface of a solid wall, you may, over the course of time, prevent a certain amount of heat traveling from the interior through the wall to the exterior. And that by blocking a certain amount of this heat, you lower the dew point of the wall, which has the effect of increasing the relative humidity of the air inside the wall. And that may lead to an increased incidence of condensation, and or it may inhibit evaporation from materials, causing the fabric on the cold side of the insulation to become increasingly wet and cold. So measuring a U value can help with that by avoiding adding too much insulation to the wall. But if we want to know more about the moisture risk, we can make measurements inside the fabric to better understand how the wall behaves with its moisture loads. That's something that we call this interstitial hydrothermal gradient monitoring, which is a real mouthful. But actually just means measuring temperature and relative humidity at 4 points, or a number of points, normally 4 points, distributed through the wall section, as well as also monitoring the interior and exterior spaces either side of the wall. So best practice would dictate that if you're considering installing internal wall insulation on a solid wall, that you should measure the performance of that wall for at least a 12-month period prior to insulating, to check whether there are no underlying moisture issues and to get a better understanding of how it manages moisture. So this graph shows 2 years of monitoring of relative humidity through the wall section at Holyrood before the wall was insulated. So 3 sensors are in the stonework, and one, that orange one, is in the batten space, that air gap. Here we're interested in times when relative humidity goes above 80%, as that's the figure that is commonly used to indicate risk, because 80% RH is one of the conditions required for mould growth. So RH above 80% in the stonework may not present a particular risk, but in proximity to timber, such as within the lining batten spaces of this wall, it may be of more of a concern if the high RH persists for a long time. So what these measurements tell us is that there are times when the uninsulated wall does go above 80%, and that this mostly occurs during the colder winter months towards the external side of the wall, which is what you would expect. However, over a 12-month cycle, you also see that this relative humidity diminishes, and when the external conditions warm up and improve, and so that this high RH doesn't persist through the wall. So there's no overall risk to the wall per se. Quite unusually, for this wall, conditions also exceeded 80% towards the internal face of the wall, particularly over the winter of 2016-17, when there wasn't really any heating in the lodge building. And as a result, the relative humidity is quite high internally and also in that cavity, that batten space. And that's a little bit concerning because, of course, that's the space which is due to be insulated with cellulose fibre. So this is the same analysis post-refurbishment, and you can see that the relative humidity is generally lower through the wall section, and it doesn't go above 80%. And that's particularly the case now at the insulated air gap between the lining and the stonework, that orange line. Relative humidity is both lower here, and also the responses are more stable. They're less volatile at that location. The RH is lower within the wall, not because the wall's been insulated, although the analysis also does tell us that there's no risk at present because of this. But the relative humidity picture has improved through the wall, mainly as a result of higher internal temperatures within the lodge from improvements to the central heating. So on average, the internal temperature has increased by 3.6 degrees post-refurbishment, and relative humidity in the now insulated batten space has reduced by an average of 12% RH. So in addition, the cellulose material is hygroscopic, and then therefore there's some sort of buffering of the moisture vapor, which is also probably helping to even out the RH response in this space. But in fact, the warmer internal temperature benefits the whole section, and even relative humidity towards the outside, that dark blue line, is lower through the wall post-refurbishment. So this sort of monitoring doesn't just have to be for walls, and it also doesn't actually just have to be for temperature and relative humidity. We can also measure moisture content, and we can do that as well as or separately through element sections. And at Holyrood, we have installed similar monitoring, which looks, in this instance, again, at temperature and relative humidity through a section of the insulated roof. The roof in this part of the lodge has been insulated between rafters with 100 mil of wood fibre, and that installation requires that there's an air gap between the insulation and the sarking boards, which are the boards underneath the slate roof covering. And here we've been asked to see what difference this air gap makes to conditions through the whole insulated section. So in one part of the roof, the insulation, we've pushed it up against the sarking boards and eliminated that air gap. So unlike, sorry, I've lost my thing, unlike that U value or that wall monitoring, this monitoring doesn't allow, it's not there to make a comparison between these kind of before and after conditions, but instead the monitoring is being used to check and test an experimental approach in this instance. So just to show you some of the results from that. So unfortunately, and this happens in the real world, we're missing some data from last winter, which of course is when the riskiest conditions arise. But the monitoring's ongoing, so we're in the process of capturing the behaviour this winter. So really, ideally, we actually need it to get a lot colder and a lot wetter in Edinburgh. So sorry, Carsten and Anne. But this is what we have so far. And it actually suggests that there's very little difference between the two treatments. This is a plot of relative humidity over time. The solid line is the installation with the air gap, and the dotted line is the installation without the air gap. And our temperature measurements show the same thing. So relative humidity does seem to exceed 80%, possibly around November, but it's also possible to see that it falls below that threshold in February, and it's the same for both types of insulation arrangements. So overall, we think on an annual cycle, we could say that there seems to be little risk to the roof with either arrangement so far. Anyway, but we continue to keep a watch on that. So before I move on to other types of measurements, I'd just like to show you another way that this type of moisture monitoring can be used in retrofit. And I've touched on this already a little in relation to U values. And that's the way that measurements of heat loss can be used to inform the modelling of energy consumption and cost and carbon savings to give more accurate results. So the RH measurements can be used in the same way. The RH measurements through an element can also be able to plot different quantities, not just RH, but you can also examine it as absolute humidity, which is another way of looking at water vapor, moisture vapor, but this time just as a weight of vapor without the addition of the temperature factor. And you can also see what the absolute humidity is doing in different parts of the wall. And then the averages of our temperature and our relative humidity measurements can also be used to plot this, what we call a hydrothermal section. And what this looks at actual temperature, that's the red line, in comparison with a dew point temperature. So that's the normally lower hypothetical temperature at which the air in the wall, in the different parts of the wall, would reach 100% RH, which of course is when condensation might occur. So we can plot these two quantities through the section, and that allows us to see if a part of the wall is approaching conditions that are favourable to the formation of water droplets and the possible deposition of moisture within the materials. So this is what a hydrothermal section looks like. This is not from Holyrood Park Lodge, because actually we didn't find a long-term risk there in that wall. So it's from a different project, but I hope you can see this converging, the temperature and the converging temperature and the dew point gradient, which is towards the external side of the wall, where we would normally expect to see it. So we're getting dew point conditions, the deposition of moisture possibly occurring towards the external wall face. So this is a similar graph, which again, it looks at averages of temperature and dew point temperature plotted through a wall section. However, The blue lines in this graph are the product of hydrothermal modelling, while the red lines are the plot of our actual measurements of temperature and dew point for the same wall over the same time period. So the hydrothermal simulation modelling was carried out by Max Fordham engineers using WFI Pro 5. The measured temperature and the RH data was combined with measured material properties for specific brick materials from the site, along with site weather data and monitored internal conditions, in order to then adjust the inputs for the model rather than just relying on the defaults available within software, in order to refine and calibrate the WFI model for this wall. So this is the plot of the wall after those adjustments were made to try to get a better fit between the output of the model and that of the real wall. So I'm just going to move between. So it's not perfect, but you can see that there is an improvement. So in this instance, the use of that real site-based data as inputs for the building simulation model can improve, and it thus gives greater confidence to the modeled predictions of the building performance for that particular building. In fact, what actually emerged from that work was, because there was still a degree of uncertainty around the performance of the insulated walls, a test room was set up where either side of this window, we measured on one side the uninsulated section of wall, which was functioning as a control, and then on the other side of the window, an insulated section. And we measured lots of different aspects of performance here, not just the hydrothermal responses, but also the U values, the internal surface conditions, the effects of the insulation on historic timbers, some of which were covered up by the insulation. And we also looked at thermal bridging at that partition wall return. What emerged from that test wall work, which lasted about a year, was because this building is highly protected, it's a grade 1 listed building, and because the retrofit scheme that was being proposed for it was really quite radical, and because it was felt that there was a degree of uncertainty around the long-term performance of the building, we ended up installing quite a comprehensive post-refurbishment monitoring scheme into a number of rooms. And in fact, this post-refurbishment monitoring was a condition of allowing the retrofit scheme to proceed. And 5 years on, we're still watching what's happening to heat and moisture through these now insulated walls, as well as looking at floor joists, floor voids. We're looking in the roof spaces, at the roof timbers, as well as monitoring other things such as room conditions, temperature, relative humidity in rooms, indoor air quality, because the refurbishment also included adding mechanical ventilation into the building. So in a similar way to our work in the roof at Holyrood, this scenario is a way of keeping watch on what is in effect experimental treatments, with the advantage that if we do start to measure adverse conditions within the fabric, there are a number of adjustments that can be made, primarily in the first instance to heating and ventilation, to try to mitigate these. The monitoring also acts as an alarm system, and we've already had one occasion where we've been able to alert the building owners to a leak that was causing the fabric to become wet. And now we're also in the process of keeping a check on whether that fabric is drying out over time after they fix the leak. So that's a kind of bit of an overview of that slightly more invasive time-based monitoring, which can be used to inform retrofit in various ways. There are some other more short-term measurements which can be used to help understand the performance of the building, both before and after retrofitting. And here is something which I assume that most of you are going to be familiar with, so a thermographic survey. So as long as these are carried out in the correct way, with suitable internal and external conditions, they are a useful way of establishing heat loss weaknesses in the building fabric pre-refurbishment, and also post-refurbishment. They can be a means to see how effective the refurbishment strategy has been and how well it's been executed. So here you have some before and after external images of the lodge, and you can see, I hope, that there's been improvements in heat losses from the glazing, at the underside of the eaves, and also the escape of heat through and around the door post refurbishment. This is some images from on the first floor. Inside the building, we're looking at internal surface temperatures on the walls here, and we can see that there's some improvement to heat loss through the walls and through the ceilings, where the surface temperatures increased post-refurbishment by a couple of degrees. However, we can also see that in the sloping part of the ceiling there, that the insulation fitted between the rafters is a little bit patchy, and there are some cold spots where actually the fit is not so good. The identification of weaknesses within the building envelope can also be aided by the use of a blower door, an air pressure fan, which we can use to depressurize the building, causing cold external air to be pulled into the structure. So while this doesn't replicate the performance of the building in normal conditions, it does help to reveal potential air leakage pathways and therefore possible sites of heat loss. So this is that front door that I showed you a minute ago, but instead now from the inside, and you can see from before retrofitting, there's quite a lot of leakage around the frame, and that the door itself, the fabric of the door itself, is cooler compared with post refurbishment, where there's work has been done to draft proof the door, but also to insulate. The insulation has been added into the panels of the door to reduce the heat loss there. So windows and loft hatches are also classic areas for air leakage, and there's some air leakage around this window before refurbishment, and but it's actually also so visible. It's still visible, but it's not really necessarily as pronounced after the windows were refurbished. And we find the same also for loft hatches. So whilst there is less air leakage around the new, bigger loft hatches compared with the older ones, there is still some leakage, and there's also heat loss through the fabric of the hatch itself, which isn't insulated. So the refurbishment has reduced air leakage and fabric cooling, but there is probably still some room for improvement here. And then finally, because we're using a blower door, we might as well get some idea of how the building is performing overall in terms of air leakage. So like heat losses, there are lots of assumptions about air leakage in older buildings that aren't necessarily borne out when you measure them. And like other in situ measurements, having an actual measured air permeability figure to input into your building simulation model, once again can give you more accurate outputs. So air pressure testing is again a useful way of making an assessment of how successful your retrofitting project has been and whether your design intentions have worked, whether they've been met. So we tested the lodge in a number of states to try to quantify the contributions that different parts of the building might be making to air leakage. So first of all, we tested the building in a fully taped condition. So that included taping up all the ventilation openings, the flues, all the loft hatches, and the windows were sealed with tape. And we carried out a number of tests, and then we untaped just the loft hatches, did some tests, then we untaped the flues, did some tests, then the windows, etc., etc. And then that was to see what contribution these different parts of the building made to the overall air leakage values. And then finally, we did a series of measurements of the building in its kind of in-use state. So that's with everything, including all the vents, untaped. So it's different from a compliance test. So the figures in at the top of the slide there show are the kind of figures you would quote if you were quoting a compliance air testing result. So before refurbishment, we had an air permeability figure of 15.29 meters cubed per hour per meter squared, which is, you know, little bit high maybe, and that's been reduced down to 11.25 following refurbishment. So there's a reduction in air leakage of 26%. So where is the air coming from? So post refurbishment, we are able to see that the air tightness of the windows has been improved. We estimated that it had been improved by these tests by about 27%, but as you then saw in the thermographic images, the windows are still quite leaky. And also the decision to open the chimney up. So the chimneys, pre-refurbishment, the chimneys actually were all closed, but there was a decision to open the flues of the chimney up in one of the rooms, and that has actually had quite a big impact in terms, not surprisingly, in terms of the air tightness of the building. And so those figures in that table there show you the different contributions that different parts of the building make to its overall air leakage. So in conclusion, I've done something that I've never done. I did something I've never done in a talk, is actually I cut some slides out because I thought it was going to go on too long. And now I'm concerned that actually hasn't gone on long enough. So if people want, I can load a different presentation and give you a couple more slides. But the reason I cut them out is they weren't strictly speaking to do with fabric, and they were to do with indoor monitoring conditions. So anyway, I'll do my little conclusion, and then if people are clamoring to know that, I'll load the different presentation. So in conclusion, I hope I've been able to show you a few of the ways that monitoring can be used to inform and benefit retrofitting, particularly with regard to building fabric, and how monitoring is a way that you can deal with the uncertainties relating to retrofitting practices, particularly for older buildings. Older buildings may not be well understood or described by the conventional tools of design and building physics used in the building industry. So measuring performance is a crucial way that we can improve our understanding of how these buildings work and how we can best ensure that improvements are made to these buildings in the name of genuinely improving their energy efficiency and genuinely reducing their energy usage and their carbon emissions. So that way we can ensure that our older historic buildings will continue to be used and stand as symbols not only of the ingenuity of the past, but also of the present, and that they will continue to contribute to the richness of our built environment long into the future. That's it. Do people want more, or have people got questions?
Right.
As you wish.
We don't actually have too many questions at the moment. We've got a couple, but I'm wondering if you've got your other slides.
Yeah,
Caroline.
I just pause. Just everyone talk amongst yourselves while I load the my other presentation, which I should have here.
I think that might be useful because we've still got a lot of time. I would add in the meantime, for those of you that haven't realized, we're recording this session, so it'll be available on the Energy Pathfinder website afterwards and on the webpage.
Okay,
for future reference. Okay.
So you can see everything I'm doing, so that's fine. And let me just get this. Oh no, hang on. Sorry, everyone. I hope it's going to be worth waiting for this bit. So this is just a little bit about, yeah. No, we don't. You don't want to see my boring notes. Let's do slideshow. Oh, I'm gonna have to blah 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 blah. Hopefully, let's go through all these. Okay, so is that okay? Everyone good? You good? No, and you're shaking your head. Can people see this? Can
we
people
don't
see
have your
slide?
full picture.
You don't have.
We've got the your view, but we don't have the slide view. If you see what I mean.
Oh, that's weird. Hang on. Let me try doing new share. Okay. 26. Let's try that one. There we go. That's better, yeah?
Yes.
Okay, good. Right. So it's one other thing that we've done at Holyrood is we've put some ambient condition monitoring in a couple of the rooms. So it's really straightforward, this. We're just measuring temperature and relative humidity in 2 of the rooms on the first floor, the meeting room and the staff room. And we started doing those measurements several years before any retrofitting work was undertaken, and then we've kept those measurements going after the building was retrofit. So we're able to make a couple of different types of analysis using these. So a couple of the things that we are looking at, there's 2 kind of analyses that we do based on these measurements. One of which is for comfort in the room, and the other of which is for fabric risk, specifically the risk to the internal wall surfaces of mold growth. So I'll talk about comfort first. The table at the top, the graph at the top, is measurements from before retrofitting was undertaken, and that kind of blue scribble is not some child that's got hold of a felt tip pen. It's the collection of all the points, data points, the temperature and relative humidity data points recorded over, I think probably that's about a year's period for one of the rooms. And you've got 2 polygons in these graphs. The outer polygon is a series of comfort indices for temperature and relative humidity, acceptable parameters, and then the inner polygon is the ideal comfort parameters, temperature and relative humidity comfort parameters. And what you can see from the pre-refurbishment measurements is not a lot of the temperature and relative humidity measurements sit very well in these comfort polygons, and there's a lot of colder temperatures and there's a lot of higher relative humidity, which really isn't surprising because this is a space that wasn't really used and it wasn't even really heated. And then in the graph below, where those points are now rendered in orange, you see there's a much tighter grouping of temperature and relative humidity data, and it largely sits within the ideal, and if not the ideal, the acceptable polygon. So conditions have improved post-retrofit, and again, that is mostly because the spaces are used and they're properly heated. Then there's about risk. There's a series of gradients in the analysis. First of which is this sort of straightforward 80%, which I talked about in terms of walls. So this is our kind of risk threshold for the possibility of the commencement of mold growth on internal surfaces. We also have a series of curves, which if people are familiar with Sedelbauer's work, which is part of the Fraunhofer Institute's moisture and mold analysis, these are expressions of what Sedelbauer calls the limiting isopleths for mold growth. So temperature and relative humidity conditions for mold growth, the growth of mold on various different mediums. And again, what you can see is in the first instance, pre-refurbishment, we have some conditions that suggest that the walls should be absolutely covered in mold, which actually they weren't, but nevertheless, you can see we have some risky conditions. And then post-refurbishment, all those measurements have dropped below these mold growth risk thresholds. So again, that we've reduced, or the risk of mold growth to internal surfaces is reduced. It's the same for the other room that we measured in Holyrood. Wasn't so bad, this room, pre-refurbishment, because it was in use, but still quite a lot of the temperatures are quite low, and there is still some relative humidity data which shows that there is possibility of mold growth. And again, post-refurbishment, there's a better fit with comfort parameters, and also it's dropped way below any risk thresholds, those 2 rooms. Now I wanted to show you, now this thing shouldn't be here, but I kind of wanted to show you what that change was. Sorry, this slide is a mess because I wasn't expecting to show this. But I kind of wanted to maybe indicate to you the difference that the temperature, the changes in temperatures has made. So these are the 2 rooms. I'm sorry, this is a bit of a mess. So these are the average temperatures of the rooms before they were insulated. As you can see, it's really quite chilly. And then this has gone up to much more acceptable, sort of 20, 19 degrees. And if you look at the maximum, our maximum RH figures, because it's more useful. So before refurbishment, we were recording relative humidity up to 100% in one of these rooms and up to 93% in the other one. And then both then the relative humidity has fallen, the maximums have fallen to way below, when, you know, like nearly 10% RH below those risk thresholds as a result of these warmer temperatures. So that's what I had to say on that particular matter. And then I could do my conclusion again, and I could start crying with impassioned plea for old buildings, but it's maybe enough. Shall I stop sharing?
Thank you very much, Caroline. That's excellent. We've got a number of questions, and I'll take them now. Sorry. There was a general question which I put to begin with, Caroline, and that's, as a general issue, how do you find that the actual measurements that you take compare to the default, if you like, assessment measurements that are used in something like the EPBD or the Irish BR calculation? How off are they?
Well, I am not going to be able to answer that question very satisfactorily, I'm afraid, Jose, because my personal experience of those kind of defaults is really limited. So ArchiMetrics doesn't undertake building simulation modeling. So we don't deal with those defaults or any of those energy assessment processes that you poor people have to do all the time. And the reason we don't undertake the modeling actually is because we think it's quite healthy to have a separation between these two disciplines, and that the two things should inform one another. But actually, if we were doing a lot of modeling, it may actually really alter the way we measured buildings, and vice versa. So it's almost like there's potentially a conflict of interest between these two disciplines. But I can answer your question in a limited way in relation to energy performance certificates and SAP and RD SAP, because I do have some experience of that, which goes back to the thing that I was talking about, which is this misapprehension of wall U values. So I was one of the people that did some of that work originally, that went and measured a whole load of solid walls and then calculated the same U value for those walls and looked at the two columns and figures and thought, my God, these are really different. And the standard process, the standard calculation is showing, you know, 50, 60, 70% more heat loss. And that I knew that U values were part of assessing the overall energy performance of a building in the SAP procedure or the RD SAP procedure. And so then went and kind of looked at what the tables of U values that are given, particularly for solid walls and stone walls and even brick walls, and realized that they're, of course, they're based on calculations, they're not based on measurements. And actually, when you talk to the people who wrote those, or the person who wrote that table, you find that they're really not based on anything very much at all. And so for a while, I was quite involved with trying to improve the methodology that's written into the RD SAP procedure. And there has now been some improvements to it, in that, for example, there is a suggestion that you should include a mortar fraction when you calculate for a solid wall, whereas before there was none, which is ridiculous. Yeah. And I haven't looked recently at the RD SAP protocol, but I do understand that there are some clauses which kind of go, look out, if it's a solid wall, you're going to have to think a bit more about it. And ideally, you should go away and find out exactly what it is, and you should have some proof, and you should maybe measure it. I don't know if it actually says that. It'd be good if it does. So I can't tell you the most up-to-date version because I basically lost the will to live dealing with the British government.
Yeah.
And,
that's great.
Sorry, that's very long. Not very helpful.
There's obviously a lot that we could discuss on that point. But I think it's probably a good idea to move on to the next question from Paul Overy. Would you like to unmute your microphone, Paul, and ask it directly? Unmute your microphone. You don't have a microphone. Okay, I'll ask Paul's question then. What would happen to the risk of interstitial condensation in solid walls if the internal spaces were intermittently quite high humidity, as in a school classroom?
Yeah, good question. Well, I think, sorry, Jose, did it say if the wall is internally insulated?
What would happen to the risk of
interstitial condensation
in solid walls if the internal spaces are intermittently quite high humidity?
Yeah.
It doesn't say.
Yeah, sure. So it's not necessarily about those walls being insulated. Well, yeah, high moisture loads, classroom, but also like, I mean, you can just get that if you have like a lot of cooking activity or higher density occupation, a lot of moisture production, a lot of people showering. Also, of course, just in the kind of the straightforward Glaser analysis of interstitial condensation, if you've got a high internal moisture load, that does increase, in theory, that does increase the risk of interstitial condensation, because in theory, most of that moisture has to get out from this high pressure, high vapor pressure internal space to the low pressure external space. And the theory is that, I mean, of course, there's ventilation and it creeps out through all the adventitious sort of gaps of the building, depending on how well sealed the building is, but that a certain proportion of that moisture load will move by diffusion through the wall fabric, is the theory. And we do see that. We also see it moving in the other direction and under certain conditions as well. So, you know, if you have got high internal moisture loads, you have to be confident that your ventilation is working, that you maybe have materials that are going to buffer that moisture vapor on your internal surfaces, like a kind of wood fiber or lime, or more open organic materials that can have that buffering effect to level out that moisture load and the diffusion of the moisture load. And actually, adequate heating as well is going to help with that. So I hope that has answered your question.
That's great.
Thank you very much.
Oh.
I changed headset.
Hi, Paul. Hi.
Hi, Caroline. It's great talk.
Oh, okay. I hope it wasn't too sort of, yeah. I mean, please ask questions, because I know it's a lot of information.
There's a few more coming. From Garish Nair. Garish, would you like to open your mic and make the question? Garish?
Yeah, my question was more related, because it was very interesting to see that there is a large variation in the measured U value as compared to like the calculated one. So it is very, I thought it was interesting. So I was just a bit curious to know whether you have some publications based on your monitoring and measurement.
Okay, Garish, I'm sorry, because I thought, like, so that's at the top of the talk, and I didn't speak a lot about that because it's been the subject of research for quite some time now in the UK. And I wouldn't say it's widely known in the UK. Actually, you know, I still come across people who are surprised by that information, but there are a number of important publications where you can find out more about it. So Historic Environment Scotland, technical paper 11, has details of that work. Then the SPAB, the Society for the Protection of Ancient Buildings, is the report that I authored with Cameron about that. And there's also, subsequent to that, work done, a little bit of work done by Historic England, and then also a larger project by the Building Research Establishment here in the UK. That's, maybe I could compile those references and pass them on to Jose, and you could go and look at that as you wish. And if you have questions about it, then of course get in touch and I'll try and help.
Yeah, that would be very helpful. Thank you.
Now, the next question is from Caroline Akiwoye. Caroline, would you like to? Yeah.
Hello, this is Caroline. Thank you very much for a really inspiring talk. It's very refreshing to hear that. I'm sorry we missed the first few minutes because our link didn't work, and I don't know whether you covered this, But some years ago, we came across a rule of thumb that recommended limiting the reduction in U value with internal insulation to avoid the risk of interstitial condensation.
Yeah.
I know this is sort of oversimplifying, but to reduce the statistical risk of interstitial condensation, would a value of something like 30% reduction in U value provide a useful reduction of risk?
Oh, you know, I have never thought about it in terms of percentages. So the figure that is used, so here in the, I don't know where you're speaking from, so apologies if you know this already, but here in the, sorry?
We're in Ireland.
Oh, in Ireland. Okay, so maybe similar. Here in the UK, they have this target for the improvement of walls, which is not, so if you're adding insulation, in theory, you should be aiming to get your walls down to 0.3 watts per meter square Kelvin. Now, a lot of people in the traditional building sector think that that is too low for a solid wall and that it will introduce risk. And so as an alternative, a figure of, there's a number of figures are given, but 0.6 is a figure that is often quoted as maybe a better figure to be aiming for. But this whole thing, and I think I probably did cover it slightly at the beginning, actually, but this whole thing is a kind of how long is a piece of string? Because it totally, I mean, it really massively depends on the individual circumstances of the building. And that even goes down to the individual exposure and orientation of the walls. So on one wall, 0.3 might be perfectly safe. And on another wall, 0.6 might be perfectly safe. And on another wall, 30% might be totally dangerous. So it could be possibly that a percentage would be a better way of doing it, but actually it also may be overcautious, because in some circumstances you maybe could push that, you know, you could push it a lot more. So I can see why in the UK people have gone with just saying it's not 0.3, it's 0.6. Although having said that, a lot of people still don't know that figure, and a lot of people, you know, a lot of architects we talk to are surprised to hear that they shouldn't be aiming for 0.3 and that maybe is going to introduce risk. The difficulty with all that is, you know, what are you going to do? You're going to measure every single wall that you're going to insulate. I mean, I think from a practical point of view, if you're dealing with a building of value, I mean, historical value that's protected, you know, in some way, and it's a solid wall, then it's probably really in your interest to try and choose the most vulnerable wall. So the wall that's maybe of greatest exposure, in worst condition, the most porous materials, the thinnest wall, etc., etc. And you take a measurement from that. And then you use that. Then you've got your worst case scenario, and you use that as the basis. And, you know, it's not crazy because you're not trying to measure all the walls. And you use that as the basis. And maybe you could look at what your 30% figure gave you, and then you could think, well, what percentage would 0.6 be, for example, and see how you, but of course the whole thing also depends on what you're intending to put on the inside. I mean, I didn't even talk about vapor open, vapor closed, because I sort of assume that that's a sort of understood in this forum. Yeah. Sorry, I'm probably not that helpful.
No, that's understandable. It is like saying how long is a piece of string, and you have to take into account climate, what the occupants of any particular space are doing.
Yeah, exactly.
That's the figure, very significant.
Yeah, but that's why I think what's interesting about this is it does come back to, if you're an architect or a surveyor or the person responsible for specifying these things, then it does come back to, it ultimately rests with your own sense of what is acceptable. You know, it almost becomes like a moral or an ethical question, you know, because there is uncertainty here. What is sensible? What do I feel comfortable with? You know, I've done the work of really trying to understand the walls. I've looked at the materials involved. I understand how wet or not they may be, and this is what I think is a reasonable approach.
Okay, that's very useful. The next question is whether you're monitoring before and after refurbishment, monitored the air quality.
Yeah, so Yeah, so because I had to talk about fabric, I didn't mention that. And actually in Holyrood Park Lodge, we're not doing any air quality monitoring, but we do that in other projects. And that project that I talked a little bit about, where we worked with WFI simulation to calibrate the model, that has air quality monitoring in it because they introduced mechanical ventilation into the space. And in that particular building, we have found no risk yet from those systems. And in that instance, all we're looking at is that by air quality. All we're looking at is actually carbon dioxide.
Well,
So you could measure. I mean, there are so many things you could measure. We can measure for particulates. We can measure for lots of off-gassing, but nobody's asked us to do it yet.
okay, that's the area that we're very interested in, the off-gassing.
Yeah.
UCs, that it's introduced into buildings through refurbishment, through the materials.
Yeah, exactly. So we did a couple of years ago, we did actually work up a project where we identified about 5 or 6 different commonly occurring chemicals in refurbishment products that we could, if it, the project didn't go ahead, which was a shame, but we were going to look at a whole bunch of things, and also including particulates. So if the building is located near heavily used motorway, also seeing what's happening in the internal air quality as a result of proximity to traffic.
Yes. Okay.
We were also wondering, and I guess you don't use WFI yourselves, but in your work with was it Happold or?
It was Max Fordham, but yeah, like Happold, yeah.
Did you gather whether or not they were happy with the range of material properties that were provided within the WFI app?
No, well, that's it. They didn't use them. So I probably wasn't very clear, but they did a number of things to try to kind of calibrate, to tweak, to refine the model. And one of the things they did is they had 3 bricks extracted from the building, and they were sent to Glasgow Caledonian University for material properties testing. And so that included like density, for all the parameters that WFI requires an input for. And then a sort of a brick, kind of like the brick, the sort of site brick, was then used in the model of the wall. Unfortunately, actually, and this is why that whole project went on to have this incredibly extensive post-refurbishment setup, is because the 3 bricks that got chosen were hugely diverse. And so it just, in a way, although it kind of helped with the model, there was still this massive uncertainty, because one of the bricks in particular was really crazy. And actually, I think they should have just chucked it as an aberration, because it had really weird contradictory properties that didn't look really right. But because of so basically the kind of the brick became, the uncertain brick became such a problem that everyone kind of went, we can't trust the model. We don't know what's going to happen in the next 100 years. So ArchiMetrics have to go and, stick their sensors all over the building, which is what happened.
We did hear that, for example, if you were looking for the properties of a particular type of masonry,
yes,
there was a limitation in WFI that it's quite good on selected German stones.
Yeah, naturally, yeah.
Limestone, but it wouldn't cover what we would find here necessarily.
Yeah. I mean, that's been a problem for ages. Every conference that ever happens about building simulation, everyone goes, but in WFI, all the materials are German. German granite is going to be different from Cornish granite. Well, maybe, yeah, and probably definitely. And there's definitely not very many. There's like 2 types of historic brick or whatever. So I think, again, I think if depending on the kind of scale of your project, the importance of the building, then there's probably an onus to go away and have those materials tested so you can be confident about your inputs. Or you don't do that. You just use the on-site modelling to refine the model. So just say, we're never going to know, we're never going to be able to describe all these materials. We're just going to make our model look like the wall behaves in real life. Then we're happy with it, and then we can have confidence in our simulation.
Yeah.
Thank you.
Great, thank you.
Thank you very much, Caroline. We just have one more announcement, really. Katrina, I don't know if you'd like to make it directly in connection with Energy Pathfinder's webinar series. Katrina, would you?
Hi, thank you for the webinar, Caroline. No, I just wanted to say that if anybody has any questions or they'd like to find the recording, that they can contact us directly, and we can add you to the emailing list to let you know about future webinars as well.
Thank you. And if you want any more information, you'll find more information on Energy Pathfinder on our website at energypathfinder.eu, and you'll find our email address where you can contact us for more information. So finally, I'd like to thank Caroline in particular for a fantastic webinar, which really puts sort of energy monitoring and the importance of actual energy performance studies in prospect. I don't think that we were clear as to how important energy monitoring can be for retrofit and for generally renovation and conservation of historic buildings, but you certainly made a very strong case for that. I'd also like to thank Historic Environment Scotland for their involvement in the Pathfinder project and bringing in this whole dimension again of energy monitoring and energy performance. And finally, NC Installation and NC Energy Hub for this series of webinars and the training and dissemination aspects of the project. And thank you all for attending. I hope you found this interesting. We welcome any feedback, and please keep in touch with our website and with us for future webinars, which I'm sure that you'll find of interest. So with no further ado, I'll say goodbye to you all. Keep well, and I hope to see you again next time. Bye.